Welcome to the deep dive. Today, we're going to try and cut through some of the noise around the modern React ecosystem. People call it full stack React, but we really want to focus on the architectural constraints and, the essential tools you need to build apps that actually scale.
And that's really our mission for you today. It's about moving past the simple hello world tutorials. We need to dig into the methodologies, the core rules, really, that manage everything from state with Redux to API calls with GraphQL and, finally getting to a robust production-ready app.
Okay, so let's start at the very, very beginning. React really boils down to two main ideas: components and the virtual DOM. And I think for a lot of people, that virtual DOM concept can feel a bit abstract. What is actually happening under the hood when a component renders?
This is so critical. When a component's render method gets called, it doesn't return HTML. It returns something called a React element. And you have to forget about the browser for a second. That element is just a plain old JavaScript object. It's a blueprint.
A blueprint. I like that analogy. So the virtual DOM is like the master blueprint for the entire UI.
Exactly. It's a lightweight, in-memory copy of what the real browser DOM should look like. And React's whole genius is this. Instead of messing with the slow, expensive real DOM every time a tiny thing changes, it just compares the new blueprint to the old one.
In memory, which is fast.
Super fast. It finds just the specific differences, and then it applies only those changes in one batch update to the real DOM. That's where all the speed comes from.
So the VDOM is basically a performance trick. And the language we use to write those blueprints, that's JSX.
Right. JSX is that essential syntax extension. It just lets us describe what looks like HTML right inside our JavaScript. It's super readable, but of course no browser understands it, so you have tools like Babel working in the background, constantly transpiling it into normal JavaScript.
Okay, let's shift from structure to data flow. The two big concepts here are props and state. I think when you're starting out, they can look really similar, but if you mix them up in a big application, well, it leads to chaos.
Their roles are fundamentally separate. Props are data that get passed down from a parent component. And the key here is they are strictly immutable.
Read only.
Totally. They're owned by the parent. The child component can only read them and display whatever's in them. Think of them as configuration.
Okay. And state.
State, which you get through this .state, is the data that a component owns internally. It's private, and it's the only place you should be storing data that's meant to change over the component's lifetime.
And speaking of that change, the sources we looked at really emphasize a design rule here, the single responsibility principle. Why is that so important when you're planning a big app?
Because complexity just explodes otherwise. I mean, if one component is trying to fetch data and manage user input and also handle all its own styling, it becomes impossible to debug. So the rule for scaling is each component should do the absolute minimum viable thing.
How do we actually do that in practice?
The best practice is to first map out your entire UI and break it into components. Then build a completely static version. Everything just gets data through props, no state anywhere. Only after that's done do you go back and figure out the absolute minimum set of components that actually need to hold state.
This is where we hit that really interesting constraint, the aha moment around immutability. We said state can be updated with this .setState, but all the experts say we have to treat this .state object itself as if it were immutable. Why? If I can change it, why should I pretend I can't?
It comes right back to that blueprint mechanism. Let's say you have an array in your state, maybe a list of messages. If you directly mutate it using a method like array.push, you've changed the array in place.
Okay, so the array now has the new message. What's the problem?
The problem is how React checks for changes. It works by reference. When you call this .setState, React looks at the memory address of the old state and compares it to the new one. If you just mutated the object, the reference, the address in memory, is identical.
So React sees no difference.
It sees no difference, assumes nothing changed, and never triggers a re-render. You get a silent failure. The data is updated, but the UI isn't. And that is an absolute nightmare of a bug to find.
So you have to be transactional. You must give React a completely new object every time.
Every single time. You use non-mutating methods. For an array, that's concat or the spread syntax. For objects, object.assign or spread syntax again. This creates a brand new object with a new reference. When you pass that to this .setState, React sees the reference has changed and knows without a doubt that it needs to update the DOM. It's a strict contract.
Right, and that strictness works when state is local. But now imagine a huge app like a social network. State starts to feel like this tangled spider web. A single click, like accepting a friend request, might need to update a notification badge over here, a user list over there.
That's a great description. We call that tight coupling, or sometimes prop drilling, where you're passing data down through 10 layers of components just to get it where it needs to go. And that mess is exactly what Redux was invented to solve. It does that by imposing even stricter architectural rules.
So Redux is basically an external, predictable data architecture. Let's walk through its three core ideas.
First, you have the store. All of your application's data, everything, lives in this single JavaScript object, the single source of truth.
I can already see how that makes debugging easier. You know exactly where to look.
Exactly. Second, you have actions. If you want to change anything in the store, you have to dispatch an action. An action is just a simple object like a memo. It only says what happened, not how to change things. Something like type, add message, text, hello.
And the third piece, the reducers, that's where the actual state change happens.
Right. Reducers are the only thing allowed to touch the state. A reducer is a function that takes the current state and an action, and it returns a brand new state. And the most critical rule, tying back to what we just said, is that reducers must be pure functions. No side effects, no modifying inputs. Same inputs always produce the same output.
Wait, okay, if the action is just a description and the reducer does the actual work, isn't that just adding extra steps, extra boilerplate? How is that overhead worth it?
It's worth it because of predictability.
Yeah.
That boilerplate is an intentional constraint. Because reducers are pure, you can do amazing things. You can easily track every single circuit change. You can implement undo trivially. And most importantly, you can perfectly replicate bugs. If a bug happens, you can just replay the exact sequence of actions that led to it. That saves so much time in a massive system.
That makes the complexity pay off. And to manage that, we often see the presentational and container components pattern used with Redux.
Yes, this pattern is beautiful for separating concerns. Presentational components are kept pure. They're dumb. They only care about how things look. They get all their data and all their behavior through props. They have absolutely no idea Redux even exists.
And the container components are the brains of the operation.
That's it. Containers handle all the logic. They subscribe to the Redux store, they format the data, and they dispatch the actions. By isolating all that logic in the container, our visual components become super reusable. And if you ever want to swap out Redux for something else, you only have to change the containers, not your entire UI.
All right, let's move on. State isn't much use if it just disappears. How do React apps talk to servers? We have to talk about responsiveness and this concept of optimistic updating.
This really gets at the hierarchy of state. You have to think of the server as the master copy of the state, and our client is just a very fast replica. For the best user experience, we assume success. Like when you send a text message, it immediately shows up in your chat history, even before the network confirms it was delivered.
So we update our own UI instantly, before the server even gets the request.
We update the local client state immediately. A user clicks like, the button turns blue instantly. Then, in the background, we asynchronously tell the server what happened. We're essentially duplicating the work for the sake of UX. If that server call fails, then we roll back the change on the client and show an error.
And that async notification part, that's usually done with HTTP requests. Fetch is kind of the modern standard for that, right?
Fetch is the big one, yeah. And the whole API is built around this concept of a promise. A promise is just an object that represents the eventual completion or failure of that asynchronous operation. It's powerful because it lets you chain things.
Right, so instead of a pyramid of nested callbacks, you get a clean, flat pipeline.
A perfect pipeline, yeah. You can define the whole sequence,
Yeah.
fetch the data, then check the HTTP status, then parse the JSON, then run your success handler. Each step just feeds its result into the next. It makes managing network calls so much cleaner.
Now let's talk about a major shift away from traditional APIs, and that's GraphQL.
GraphQL completely flips the script. In a traditional REST world, the server defines rigid endpoints. You ask for a user, you might get back 50 fields of data, even if you only needed 2. That's called overfetching.
And GraphQL solves that by letting the client decide what it needs.
Exactly. The client sends a query that specifies the exact fields and even the relationships it wants. The server schema defines what's possible, but the client asks for what it needs. This cuts down payload sizes massively. It's a huge win for performance, especially on mobile.
And Relay is the client-side framework that's built specifically to manage all the complexity of working with GraphQL.
It's a really powerful system. With Relay, you define a component's data needs using fragments. Then, when you want to change data, you use mutations, which are like actions sent to the server. But a key part of that mutation is you also have to tell it what data to return after the change, so Relay knows how to update its local cache correctly.
What about huge data sets, like an infinite scroll on a social media feed? How does Relay handle that efficiently?
That's where cursors come in. Instead of just using page numbers, which can be unreliable if data is changing, Relay uses an opaque cursor. It's basically a pointer to a specific item in the list. This guarantees that when you ask for the next page, you get a stable, deterministic set of items right after that cursor, even if new items have been added to the top of the list in the meantime.
So once we have our data flow and API sorted, we need tools to manage the actual code base as it grows. Let's talk about the build process.
The modern standard for organizing code is ES6 modules, using import and export. This lets us break a huge app into small, manageable files. But browsers don't natively support this yet, so we need a build system. And the core of that system is almost always Webpack.
Webpack, the bundler, what's its real job here, beyond just sticking JavaScript files together?
It does everything. Webpack treats all your assets as dependencies. Your JS modules, sure, but also your CSS files, even images. You can literally write import.styles.css in a JavaScript file. Webpack then processes all of them and bundles them up, usually into a single optimized bundle.js file for the browser. And in development, it serves this file from memory, which makes for incredibly fast reloading.
Okay, with the code organized, how do we get confident that we're not constantly breaking things? That brings us to testing with tools like Jest and Enzyme.
Jest is the testing framework, but to really test React components well, you need a utility library, and that's usually Enzyme, which came out of Airbnb. And the real secret sauce in this world is an approach called shallow rendering,
Why is shallow rendering so important? Why is it the preferred way?
because it tests your components in total isolation. When you shallow render a parent component, it doesn't actually render its children. It just notes that they're there. This means your test is only focused on the component you're actually looking at, not its dependencies. It gets rid of all the noise and makes the test much more reliable and way, way faster.
And what kind of testing style does that enable?
It enables a very clean, behavior-driven style. You can simulate user events, like input.simulate, and then you just make assertions on the result. Did the state update correctly? Did a new component appear? You're testing that the component behaves the way you expect under very specific conditions.
Finally, we've built this beautiful, tested web app. How do we take this knowledge and apply it to mobile with React Native?
Well, the core ideas, components, props, state, they all carry over. But the rendering target is completely different. You're not making DOM elements anymore. You're creating real native UI components. So a single difference is, on the web, you have onClick, but in React Native, you use onPress.
And how do you handle the overall structure, navigating between different screens?
You use navigation components, like the navigator component, which manages a stack of screens or scenes. And you can configure the transitions for those scenes to get that native feel. You can specify, for instance, that a certain screen should slide in from the side or that it's a modal that should float up from the bottom.
I understand the styling is completely different, too. There's no CSS.
And none at all. Styling in React Native is all done with JavaScript objects that you pass to the style prop. And because CSS properties have hyphens, you use camel case in JavaScript, so font size becomes font size. The best practice is to use the stylesheet.create helper, which validates your styles and can apply some performance optimizations behind the scenes.
So we've really traced the entire path, from a single component through complex state management and APIs, all the way to a tested cross-platform mobile application.
And what really stands out, I think, is that the high-level methodology is what really matters, not the specific tool. It's always about breaking down the UI, building a static version, identifying where state needs to live, and centralizing data flow. Whether you do that with Redux or GraphQL or something else, that core structured approach is the constant.
It's the intentional constraints and that focus on predictability that ultimately saves you from being overwhelmed by complexity.
Precisely. And that brings us to a final thought for you to chew on. If we agree that the server is the master holder of state and the client is just a fast, optimistic replica, how should that hierarchy change how you write your tests? Should you prioritize testing the immediate local client state updates, that instant UI feedback, or should you focus your tests on ensuring the client successfully communicates with a mocked version of the server? Where should the bulk of your confidence testing actually live?